Hi, in this video, we want to take a look at partition matrices, also called block matrices, and then we'll start talking about matrix rank. Rank is a huge, important concept, and that's one that we will always need to be kind of keeping in the back of our minds as we work through the problems in this course. Now, partition matrices, block matrices, those really are just a notation trick to make some problems easier for us. We could probably get through this course without it, but we're going to go ahead and cover it just so that we have that tool in their tool belt. All right, so for some problems, the notation, actually for a lot of problems, the notation you use in mathematics makes it a lot easier or a lot harder depending on how you go about it. For plenty of problems, if you choose the right notation to work on a problem, it's relatively easy, relatively simple to get through your proofs. And it's easier to understand such proofs when the author chooses a good notation. But the flip side of that is if you pick poor notation, it can be extraordinarily difficult to get through the proof. And so this is true for a lot of people who are, relatively new to proofs, is that they get used to certain notations, certain ways of writing out what they're working with, and they don't want to go away with that, and they try to use the conceptually easier notation for them to understand, but that's not the easy notation for the problem. So we need to be able to bounce back and forth between whichever notation gives us the easiest the easiest gradient, if you'll put it that way, for the problem. All right, so let's go ahead and think about block matrices. I like calling them block matrices. That's what I learned them as. But if you want to call them partition matrices as the author does, whatever, it's all good. All right, let's take a look at the matrix A. So you'll notice that I've got a vertical line and a horizontal line. And you can see that these lines break up the matrix into four submatrices. We have a 1 by 1, a 1 by 2, a 3 by 1, and a 3 by 2. And so we could think of it as this 1 is a submatrix, so I'll call it A11, and then I'll say this 2, 3, this is a submatrix A12. This vertical vector we'll say is A21, and then A22 is the biggest one of the four. And so we can kind of visualize this matrix as being four submatrices in this format. Now, when I do the block matrix notation, usually there's some feature of the matrix that it makes it very obvious why we would partition it that way, why we would choose the blocks in that manner. If we can, in usual, we like to have square blocks because that'll make a lot of our notation easier. A lot of our formulas will be easier to work with. All right, so if I have multiplication of block matrices, something about the rest of the time that we're doing stuff in this concept is that it is implied that the matrices are conformal. That is, when I have multiplications, columns, then rows match each other. That multiplication makes sense. If multiplication doesn't make sense in the problem, this notation does not apply. So let's say that we have A is a 2 by 2 block matrix. B is a 2 by 2 block matrix. Notice that we're not saying what the dimensions of the submatrices are. We just say that they're submatrices. That's it. Well, in this situation, A times B is equal to this particular multiplication where I have A11, B11, A12, B22, and they're being added together. Sorry, A12, B21. When I look at the lower left-hand position, I have A21, B11, and I have A22, B21. We have multiplication, then we do addition. Hopefully this feels familiar compared to regular matrix multiplication. It's very similar. Now remember, we have to have conformal dimensions of these submatrices every single time, or this does not make any sense at all. All right, well, we can actually make this a little bit easier for us in terms of notation, that if I have A, B, I, J, so here this is the block matrix IJ after multiplying A and B, well, that's just going to be the sum of the matrices being multiplied together, very similar to how we had it in regular matrix multiplication. So it's going to be block AIK, block BKJ multiplied together. That's a block. Remember, that's it. That is two matrices being multiplied together, and then we add up all the resulting matrices. Now, you'll notice something about this is that when I get to this point, I'm doing addition. When I do addition, remember, we have to have the same dimensions of the entire matrices to be able to do matrix addition. So there's a lot of things going on in this formula. We're saying that the column of AIK is equal to the number of rows of BKJ. These are matrices, remember, we're multiplying them together. So for multiplication to work, columns have to equal rows. Then we're going to go through and we're going to multiply all of the corresponding blocks together. We're going to add them all up. When I add them all up, I have to have the same number of rows and columns every single time. And so this only makes sense if we have, like, dimensions are very consistent in this aspect. And a lot of times, just to make things easier, if we can, as authors, we tend to like to make all the submatrices square because that forces this formula to be coherent. All right, block diagonal matrices are block matrices where we have 0 off of the diagonal. So remember the diagonal matrices where we had entries on the diagonal and then 0 everywhere else? Well, here we have block matrices on the diagonal, they're blocks, and then we have 0 matrices everywhere else. So here, this represents a matrix of zeros. This represents a matrix of zeros. This represents a matrix of zeros, and so on. Now, these matrices along the diagonal, they may be diagonal, they may not. We don't know. They could even be 0 matrices. They could be anything. We just know they're not the 0 matrix. Why do we like formulas like this? Well, these are going to be, if we can get certain problems into this format from a numerical linear algebra point of view, I can solve a lot of problems very, very quickly because of this special format. And so that'll be important if we get to like the latest material in this course. Probably won't get to it though. There's also tridiagonal, and tridiagonal is another good format to have from a numeric computations point of view. All right, so let's say I want to use block matrices and matrix and vector multiplication. So what I'm going to do, let's go ahead and say that A is a block matrix of 2 submatrices next to each other, and we're going to say that B is a vector, and I'm going to represent it as 2 vectors on top of each other. All right, well, A times B, we know what that is from the previous video. That's going to be A1 and A2 multiplied by B1, B2 in this format. Well, I know that's going to be block matrix A times vector B1, block matrix 2 times vector B2, and then I add them together. Hopefully this is not shocking at this point. Okay, well, what we can do with A, you know what I'm going to do? I'm going to say that each column is a block matrix. And for B, I'm going to say that each row is just 1 entry because it's a vector. So this is a bunch of scalars, and this is, I'm representing A as a collection of column block matrices. Well, if I do that, then the multiplication we can see, and this is just rewriting A, I can see that this is B1 times vector A1, B2 times vector A2, and so on, BP vector AP. There should be an arrow right there. Okay, this is what we call a linear combination. Anytime I have coefficient, multiplication, addition, coefficient, multiplication, addition, I do that repeatedly. I have coefficient plus something, and then I do addition, coefficient times something, and I keep on going down the line like that, and something is algebraically the same type of item every single time, then that's called a linear combination. And so we can see that here, anytime I have a matrix multiplied by a vector, we get a linear combination of the columns of A. This will become very important in a moment. All right, so now let's do this a different way. Let's say I'm going to take the vector A. So remember, vectors go like this, or up and down. Let's take the transpose. I switch it to sideways, and I'm going to multiply it by a matrix on the right. So I have a row vector, scalar to scalar, 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 all the way down. And then I'm going to represent this B as a bunch of row vectors. So B1, B2, B3, all the way down to Bn. Okay. Well, if I go through and I do my multiplication, what I'm going to see that I have the B1 vector times A1 scalar, there should be a 2. Nice thing about a whiteboard is you can just walk up and put 2 right there, real easy. B2 vector times A2, keep on going down the line, Bn vector times An, and I'm taking the transpose. What ends up happening is that we can see that this multiplication we get here is a linear combination of B's row vectors. Now the block transpose is similar but different from the transpose that we've been talking about so far. If I have A1, A2, then the transpose of A is the transpose of A1, A2. And how that ends up is that, remember, rows become columns? Well, the number of rows here, the number of rows that A1 has is going to be the number of columns. Well, that's going to be the number of columns in A1 transpose. All right, and the number of columns I have all together between these two are going to be the number of rows when I take the transpose, which will be the number of rows I get from the transpose of these together. So here, they're side by side and they get stacked, and boom, we've got a transpose formula, real nice for us. Now, things get a little bit more complicated. It doesn't always work out in more complicated block matrix situations, so we're just not going to talk about it. We're going to keep it simple, just with 2 block matrices side by side for transpose at least. All right, rank. Rank is a critical idea in linear algebra, and it is absolutely super important to us. All right, rank, the idea, ultimately from our point of view as statisticians, what rank tells us is, do I have any variable columns that are redundant? That's what I want to know. So mathematically, redundant is not as obvious as it would be in other situations. But so the idea of a low rank matrix is that I have something that is redundant. I don't need it. So if I was doing machine learning and I had a low rank predictor matrix, then that would mean I would have a variable that is redundant, which if it's redundant, I don't want it in there because it's going to slow down my computations. It might make my computations less accurate. That's actually a huge issue with linear algebra, with overfitting. So when we think about rank, this is kind of like a first step to understanding getting rid of variables we don't need, because we need like some kind of mathematical justification structure for saying when something is redundant. First thing I want to say is linear dependence. All right, dependent, linear dependent. This is the one we don't want in a predictor matrix. Vectors, so these are all column vectors, are linearly dependent if there exist coefficients C1, C2, C3, Cn, such that if I take a linear combination and the linear combination is not 0 and the C's are not all equal 0 to themselves. Okay, this is going to take a few times to reiterate. There exists a linear combination, there exists coefficients such that the linear combination is 0, but the coefficients are not all equal to 0. That means one or more is not 0. Linearly independence is saying that the only solution to this equation is for all the C's to be equal to 0. Linearly independent means that I have some vectors, and the only way I can get 0 from a linear combination is if all of the coefficients are equal to 0. I'm going to say that again. Linear independence is where I have some vectors, and I can find coefficients that solve this equation, but that solution has to be all equal to 0. Independence means that all 0 for all the C's is the only solution to this equation. Linearly dependence means that this equation equal to 0 has a solution other than all zeros for the C's. Okay, so if these are linearly dependent, then at least one of the AIs can be expressed as a linear combination of the other vectors. Well, let's think about this for a moment. Let's say that I have this equation, and not all of the C's are equal to 0, right? Okay, so let's pretend C2 is not equal to 0. Well, what I could do, I could pick up the C2 and A2 part, and I can move it over here, right? I could do that. And C2 is not equal to 0, and A2 is not equal to 0. That's implied on this. All the vectors in this conversation, all the A vectors are not equal to 0. Otherwise, this is a pointless conversation. It's like the stupid case, so we don't even talk about it. All right, so if I move the C2 over and C2, A2, I move it over, C2 is not equal to 0, and that means that I can get the A2 vector using all of the other A's. If I can get the A2 vector using all of the other A's, then I don't need A2. So it's redundant. It's not helping me on my problem, which means that if I use it, I would be overfitting on my model. That's bad. Okay. All right, the rank of a matrix is the number of linearly independent columns of A, and it's also equal to the number of linearly independent rows of A. Okay, so think about that for a moment. It's the rank of a matrix is the number of linearly independent columns, and it's simultaneously equal to the number of linearly independent rows. Well, a matrix can have a different number of rows than columns, right? Okay, so if I have 100 rows and 3 columns, then if I only have 3 columns, the most linearly independent columns I can have is 3. Well, this is saying that simultaneously, the most linearly independent rows I could have is 3 also. Kind of a big deal. So a matrix is called full rank if the rank of A is equal to the minimum of its 2 dimensions. All right, the rank of A is always less than or equal to its number of dimensions, or the dimension numbers. All right, so let's go ahead and look at this matrix, and I try to pick the simplest ones I can imagine. I'm not creative with my numbers. A is equal to 1, 2, 3, 4, 5, 6. 2 rows, 3 columns. Okay. There are 3 columns, so you know the rank is at most 3. And here, the number of rows is 2. You know the rank is at most 2. Okay, so you know that right off the bat, at most, the rank is 2 because that's the less of them. That's the lesser. Okay, so the rank is either 0, 1, or 2. 0 isn't going to work out because 0 is only when we have like the 0 vectors going on. So it's 1 or 2. Let's take a look. All right, if I am able to express a linear combination where it's not all equal to 0 to get the 0 vector, then is linearly dependent. Well, I look here, if I go -1 times the first column, 2 times the second column, -1 times the third column, I get 0. Go ahead and do the algebra, it works out. All right, and if I look through here, what I could do, I could take this 3, 6, and I could move it to the right. If I move it to the right, I can see that -1 times 1, 4, and 2 times 2, 5 gives me 3, 6. I just pick it up, move it over. Okay, so that tells me that the 3, 6 column, from a statistician point of view, the 3, 6 column is redundant. It has no useful data in it from a linear algebra point of view, from a linear regression point of view, because these two vectors cover the information that's already in here. Okay, well, then the next question is, it's rank 2 or it's rank 1 now. Can I get 2, 5 out of 1, 4? No, I can't. So it's rank 2. These are two linearly independent vectors. All right, let's look at another example. I've got 1, 2, 2, 4, 2, -1, 6, -3. Check out what happens when I multiply them together. I take two things, I multiply them together, and I got 0. I got the 0 matrix. Does that make sense? Wait, what's going on? All right, so if I multiply two things together, and I get the number 0, if I'm talking about regular multiplication now. If I have two regular numbers, I multiply them together and I get 0. That tells me at least one of the things in the multiplication is equal to 0, right? We're going back to like 3rd grade or something like that. Well, here it's a little bit trickier. Here I multiplied two non-zero matrices and got the 0 matrix back. Why is that? Well, let's dig a little bit deeper. Let's look at these two columns. 1, 2, 2, 4. 1, 2, and 2, 4. If I multiply the first one by 2, do I get the second column? Yes, I do. Yes, I do. Okay, so what's going on is that this is a rank 1 matrix. All right, this is a rank 1 matrix, and this column is kind of like redundant, right? All right, if I look here, 2, -1, and 6, -3. If I multiplied the first column by 3, do I get 6, -3? Yes, I do. All right, so what's going on is that these are both low rank matrices. So it's possible to get all zeros out of a low rank matrix, because what we're setting it up is that I'm going 2 times this, make it negative. So you notice if I multiplied this by 2, multiplied this by -1, and then I add it together, it would cancel out, right? 2 minus 2 is 0. 4 minus 4 is 0. If I execute this multiplication, I'm going to get 0 and 0. Here, it's really the same thing, but I'm just multiplying by 3. Multiplying by 3 isn't going to change zeros, so I get the 0 matrix. All right, for this next theorem, I'm honestly not satisfied with the author's proof. I would have done this more similar to how my abstract algebra taught me this material, but I'm going to roll with it. If you don't like, if you want this to be fleshed out more, I'll do it. I would have actually written out the linear combinations, but to be consistent with the author, I went ahead and just stuck with his technique. Okay, so if A and B are conformal, so remember, conformal means I can just do the multiplication, that it makes sense. Then the rank of A times B is less than or equal to the rank of A, and the rank of A times B is less than or equal to the rank of B. So the rank of A times B is less than or equal to the minimum of the rank of A with the rank of B. Okay, so why is this true? The columns of A and B are linear combinations of the columns of A. That comes back from the multiplication we actually did a few moments ago. Thus, the columns of A, B are in the span of A. So here, when I say span, it's basically linear combinations. All the possible linear combinations of A include A times B. Hence, the rank of AB has to be less than or equal to the rank of A. So what we're saying here is that if I was to consider all of the possible linear combinations of A that I could possibly get, AB is inside there. All right, so here's all the possible linear combinations I can get from the A matrix. AB is somewhere stored inside that. Okay, so if A is contained inside there, then, or sorry, AB, if AB is contained inside that, inside that region, then what's going to happen is that the rank has to be smaller or equal to the rank of the original set. Now, for the rank of AB being less than or equal to the rank of B, we repeat this argument, but with row vectors of B. Now, the next part of the theorem, and we're not going to prove it here, is that if B and C are full rank, then the rank of A times B is equal to the rank of C times A, which is equal to the rank of A. So multiplying by full rank matrices, we do not lose rank. If we multiply by full rank matrices, we do not lose rank. Now for any matrix, the rank of A transpose A is equal to the rank of A transpose and equal to the rank of A. This will be important later. So the rank of A transpose A is equal to the rank of A transpose, which is equal to the rank of A. All right, that's all I've got for us. So, oh, homework. Students have been asking me. In Canvas, I've been posting due dates for these lecture videos. That's when I want you to watch the video. That basically, I'm just trying to tell you, hey, this is when you should be watching this to stay on top of the material. I want Canvas to kind of like announce, I set it up as an assignment because I want Canvas to bug you and let you know, hey, yeah, you have a video to watch. Now, when to submit your homework questions, just do it, you know, like within a few days. I would prefer if you submit before I post the next video. I'm going to try and do a Monday, Wednesday, Friday schedule, but you know, just keep on top of it. If there's a hard, heavy deadline, I'll announce it in an announcement to make sure you know when it's really important to, like, if I have like towards the end of the semester, I'll be kind of hard-nosed about due dates because I've got my own deadlines I have to meet. But for now, early in the semester, you know, just keep submitting. Things will be good. Well, let me know if you have any questions. Take care and goodbye.